Hello, today we are going to start a new topic called as Cauchy's integral formula. So what is Cauchy's integral formula? So let's start. So let us write the statement for the Cauchy's integral formula. Now if f of z is analytic within and and closed and a closed curved C, and if A is any point, so our f of z is analytic within and a closed curve C if A is any point within C, then f of A is equals to 1 upon 2 pi I integral to z. It will be f of z divided by z minus A dz. So we have to get this equation. Okay, so let's start our proof. Before that, I'll just draw a diagram, simple diagram. So which type of diagram is this? Whether it is a simple or multi-connected curve region. Okay, simple. Okay, now here in this part, this is a circle C. Okay, path is along the clockwise. C is along the clockwise. Okay, now coming out this way. This is in this. Then C1 is another circle, and let A be the center of these curves, and Z, this region we denote it as a Z. Okay, now so we'll start the proof. Now consider the function. So we are considering a function f of z upon z minus a, which is analytic. So this function is analytic at all points. We are considering these things, okay, with C. So with C means this one, except with the point A, which is as center and radius is R. So also we have drawn a circle. We call it as a small circle C1, which is lying entirely within C. So as I said, the f of z, we have considered this is analytic. F of z upon z minus a, it is analytic in the region between C and C1, hence by Cauchy's integral theorem. That is theorem and formula is different. So we are deriving formula now. Theorem for multiple connected regions, we have, so what we are having is integral, region is C, f of z upon z minus a into dz, which is equals to integral second circle, that is C1, f of z divided by z minus a into dz. This term we can write it as integral C1 f of z minus f of a plus f of a. We have taken it minus and plus form, okay? Z minus a, this is into dz. Then integral C1, same circle, C1 f of z minus f of a divided by z minus a into dz plus integral f of a into dz divided by z minus a. Let me mark this whole as equation number 1. Now for any point on C1, so for any point on circle C1, we are getting it as integral C1 f of z minus f of a divided by z minus a dz. So we'll get something like this: integral within the limits 0 to 2 pi f of a plus r e I theta minus again f of a I r. This is a f of a f of z term, this is f of a term, okay? So f of a I r e raised to I theta whole is multiplied by d theta. This is numerator. The denominator is r e I theta, okay? So why we are getting these terms here? We are considered, since z minus a is equals to r e I theta. So our dz comes out to be I r e, derivative of this with respect to z we will be getting is I r e I theta into d theta, okay? Now so again integral 0 to 2 pi, so what we are doing is we'll take out this term as common, and then we'll just cancel out these common terms, and let's see what we are getting it here, okay? Bracket is here. Okay. So we will get it as f of a plus r e I theta minus f of a, and the remaining terms is I d theta, that is equals to 0. So this, we are at the denominator part we are having r e I theta, so numerator also we are having I r e I theta, so I remains these terms gets cancelled. So this is a result of this. So we are having only I and d theta term. Okay, now where r tends to 0. So now here in this case we are having the r term which is going towards the 0. So as a result what we are getting it is here is integral c1 dz upon z minus a. Okay, this term is up till here, it is done. Okay, this we have solved this part. Now we are solving the other part. Which part? That is dz upon z minus a. So this part we have solved now here. Now this part we will be solving it here now. Okay, so which is equals to integral 0 to 2 pi I r e I theta d theta divided by r e I theta. So again here in this part, this term gets cancelled out. So we'll have only I and d theta. So which is equals to integral 0 to 2 pi I d theta. So what we will be getting is I theta within the limits 2 pi and 0. So which is equals to 2 pi I. Okay, so from equation number 1 you can see that we have solved this first part, we have solved the second part. So now putting the values of the first part, then putting the values of the second part in the equation number 1. So we'll get something that is our solution to our Cauchy's integral formula. Or you can say it's a Cauchy's integral formula. So putting the value of the integrals in RHS of 1, we have integral C f of z dz upon z minus a, which is equals to the first part, this is 0 plus f of a into 2 pi I. As a result, this f of a is equals to this term, I am bringing it here, 1 upon 2 pi I, again integral c f of z dz divided by z minus a. So hence we have given a proof for the Cauchy's integral formula. Okay, so we have completed with a statement and a full proof for the Cauchy's integral formula. Now next topic which we are going to start is a Cauchy's integral formula for the derivative of analytic functions. So just a simple things which we have to write it as Cauchy's integral formula for the derivative of an analytic function. So let us write some statement for this first and then we'll start the proof. It's just a 2-line proof as we are having the Cauchy's integral formula. So what is the statement? If a function f of z is analytic, so if our function is analytic in a region, so it is a analytic in a region R, then its derivative at any point z is equals to a of R is also analytic in R and is given by f dash of a is equals to 1 upon 2 pi I integral f of z upon z minus a the whole square dz, where c is any C is any closed curve in R surrounding the point Z is equals to E. So as we have our previous proof, what was there? So by Cauchy's integral formula, what we are having, f of a is equals to 1 upon 2 pi I integral c f of z upon z minus a into dz. So let me mark this as equation number 1. So what I am doing is differentiating with respect to a. Differentiating equation number 1 with respect to a. So what I'm getting it as, f dash of a is equals to 1 upon 2 pi I integral c f of z. So differentiating with respect to a, so 1 upon 1 minus 1 upon z minus a into dz. So what I'm getting it as, f dash of a is equals to 1 upon 2 pi I integral c f of z divided by z minus a the whole square into dz. Okay, and if I want to take out the double derivative of this, so it will be double derivative again differentiating with respect to a. So differentiating with respect to a, we get, so same thing, double derivative is 1 upon 2 pi I integral c f of z, and that will be f of z upon z minus a the cube. So this is square, this becomes a cube into dz. So in general, what we can write it as, the Cauchy's integral formula for the derivative of an analytic functions, it is general. So f double dash, whatever derivative it is, so it is 1 upon 2 factorial n factorial yeah, here it was 2. Okay, it is 2 factorial here. So n factorial upon 2 pi I integral f of z divided by z minus a n plus 1 into dz. So as we have got the proof for the Cauchy's integral formula. Now next, let us start with one problem. Thanks for watching.